Okay, so hopefully we are at least reasonably close to working. So my tablet's working just fine. The power cord is dead. Or at least somehow I'm not being able to supply power to the tablet. I don't know what's going on with it. So it just reported the minute before I started walking down to class that your battery's about to die. I'm like, oh, great. I haven't plugged it in right. Oh, fiddle with the plug and fiddle with the plug. No. It's the cord. It's not supplying power down here either. But anyway, so hopefully this will be reasonably close to what I was originally intending on presenting. Unfortunately, I'm not going to be able to see the chat window, so I'll be alt-tabbing over that every now and again. We don't have much important to talk about today, just a lab and a few notes about a test. So, anybody have any questions they want to ask? What's the answer? Brad.
On lab 3, when we're supposed to be displaying for our programming, we're doing it for really low frequencies. What are we supposed to be displaying for like 1.5 hertz?
So for the question is for really low frequencies, what are you supposed to be displaying? You're supposed to be displaying what the frequency is.
For 1.5 hertz, are we supposed
Put
to
it 1.5.
1.5?
Yeah. Or if it's like 1.5 hertz, yeah, you should not be printing out integer values there. You should be printing out a floating point number. Another question. Okay, so we finally, as of this morning, have a room. They had to scour all over campus in order to get us a room for our review session for today at 2:30. It will be in Library 163. Okay? That is a room that has WIMBA. Knowing my luck today, I can't vouch for how well things are going to work with the technology, but the idea is that I will be broadcasting this and I'll record it as a lecture, so if you can't come today, the Library 163 P5780 review. Today at 2:30. Okay? Questions about that? Anybody taking a look at the practice exams yet? Okay, so I will try to type these down. I had all these written up on notes, but like I said, they died anyway. 05, 06 notes or exams. They reference the Onset PT8. That's a different board. Okay? So the questions are relevant. They're just phrased in terms, and they have, the code that I provide you for Lab 3 Phase 2 looks very different in the Lab 3 Phase 2 that I gave out in 2005 and 2006 because we were using a different board. Okay? But the types of questions that I ask are still relevant. Like, for example, on the 05 or the 06, I ask you to implement an interrupt-driven output routine. And I ask it again in the 07 exam, but phrased in terms of the TS7200 board. Okay? So when you're working on the previous exam, sometimes you'll have to crane your head to one side and squint your eyes and try to figure out how to shoehorn the question into a TS7200 question. Which shouldn't be too hard. Excuse me. All right, also, 05, 06 exams, covered chapters 1 to 6. We're only covering chapters 1 to 4. Okay? What this means is no exceptions, exception handling. Macros are fair game. Okay? So when you're reading through, both the 05 and the 06 exams have some questions asking you to do exception handling with macros. Look for those on the next midterm, not on this one, because we aren't doing exception handling yet. You haven't had the most fantastic book assignment yet. All right. there's the other thing is that every time I've taught this class, I've given out homework assignments, but in the interest of trying to reduce the workload somewhat, I have not given you guys homework assignments from the book. I've just given you the labs. I have downloaded from the last year's homework assignments what the assignments were, and I was going to hand those out to you as suggested problems to look at. I will expect you to have read the book when you take the exam. I will expect you to have listened to the lectures, so it's not all just what was in the lab. Most of the exam will be weighted towards what is in the lab, but I will expect you to have at least browsed the questions that I'm going to send to you. I had them while I was going to give them to you all right now, but anyway, with the unfortunate snafu, they are on a journal file that I will have to send out via email. Okay. Well, may I borrow your book, Tony? Looking at this stuff, I'll be able to tell you which ones they were. Let's see. Try the following problems. We'll put that in quotes. Again, you don't have to do these. They are not for credit. They're not going to appear verbatim on the exam like this. And again, the exam will be weighted towards the lab. 3.3, 3.4, 3.9. Then in chapter 4. I want you to take a look at 4.2, 4.3, 4.7, 4.9, and 4.8 in Ada. Doesn't have to compile. Okay. So those are problems that I've handed out as homework assignments before. Take a look at them, peruse them, understand what's going on. One thing that's going to frustrate you about our great textbook, the book is fantastic in the sense it's got a whole lot of information and exposes you to some things that I don't directly touch in lecture, but I still expect you to be on top of things with it. Some of the questions are more targeted towards grad school in the sense they're not turnkey. They don't have quantitative responses. They're going to say, well, consider you've got two programming languages. Why is this feature better than that feature? And the answer isn't directly in the book. And you're going to have to read the book and analyze the information there and come up with an argument. So some of these questions ask you to argue a point. And so when I've given these out before, I just expect a valid argument to be able to make an argument and to support your point that you're trying to make. So just as long as you're able to make a reasonable argument, even if you're way, way off base, you would have at least gotten some credit on these problems. There are wrong answers, like with everything, but there are a myriad of right answers. Okay. Questions about this? In the review session this afternoon, please make sure you come prepared to ask questions. I am not going to give a formal presentation. Okay? I am going to be there to answer questions you bring. I will be prepared to go over and give you strategies for how to solve some of the midterm questions, depending on what you want to know about. Okay? But I'm going to stand in front and ask for questions, and you guys give me questions, and when we're done, we're done. Or when it reaches 3:30, when I have to be in my office for office hours, we're done. Okay? So make sure you look over the past exams and come prepared to ask questions, and I'd be happy to answer them. All right. So now comes the advantage or the disadvantage of Microsoft using Microsoft journal files. There we go. I had to download the viewer and install it. Okay, so this is Lab 4. These are the notes from Lab 4 that I started lecturing on last time. Lab 4, Lab 3 is due today, right? So you can hand it in tomorrow. There is a provision for handing it in tomorrow. It just might impact your grade a little bit. 40%, I think. Okay. If you remember Lab 3, the whole goal of what we're doing, we've got two goals. We're trying to model in simulation a DC motor, and then we are also modeling a velocity sensor using the TS7200. So this is kind of the setup for Lab 3 Phase 2, or at least what we're thinking about when we're thinking about Lab 3 Phase 2. We've got a motor here that goes to a velocity sensor. The velocity sensor picks out a square wave with 1 peak per pulse, 1 peak per revolution, 1 pulse per revolution. That goes into a DIO input line to the TS7200, and the TS7200 detects every time that we get a peak, a low to high transition on that digital input line. We also have a timer interrupt that fires periodically. And because we can know the beginning time or differences in between how many timer periods have expired since the last peak that I saw, I can detect how much time is elapsing between peaks. Okay? And again, this assumes that your timer is firing. So does this assume that your timer is firing more frequently or less frequently than your velocity sensor? Okay. And that's the problem of the low hertz rate, is if your timer is not. So if that assumption is flipped, I guess that doesn't make any sense. If your if the code is written such that it assumes that you're having multiple pits per interval, then it's easy to figure it out. It's easy to detect how much time is elapsed between peaks. If the reverse situation is true, if you've got multiple peaks per timer interval, and that's what our code does. It assumes you've got multiple peaks per timer. That's not true either. I'm all messed up today. But anyway, you've got one counter that's going as a square wave. You can kind of consider the timer as a square wave. You've got one of the square waves where you've got multiple peaks per not frequency, per period. There we go. Per period. If the reverse is true, then you can't get a decent measurement. You guys know that, even though I'm bumbling through the explanation of it. Okay. Lab 3, we're going to close the loop around the motor. We've got to answer a couple of questions. How do we emulate a motor? Well, we either use a motor or we can use a function generator to pretend like it's a motor. So we're going to use a function generator since we don't have motors and we don't want to blow up motors. Okay? We need to know how to control the frequency and the shape and the level of the square wave of our square wave signal. We know how to do that with a function generator. How do we do it? Well, we use knobs and buttons. We adjust and tune the frequency output of the square wave. Okay? The question then becomes, how can I use another device to adjust the frequency of that square wave with the function generator? Okay? So a function generator typically has what's called a VCF input, voltage controlled frequency. Sometimes you see this as VCO. But this is an input. Sometimes it's on the front of the function generator. Sometimes it's on the back of the function generator. But what it lets you do is it'll let you apply a DC signal to the function generator. And if that DC signal is non-zero, it will impact the frequency that the function generator generates. So it's like you're using a voltage input to turn the knob of the function generator when it says adjust the frequency that it's outputting. Okay? So you can apply a voltage to the VCF input and it changes the frequency without you having to touch the function generator. So this is like you trying to adjust it without using your hand. So you stare at it hard enough or you come over and you tweak your VCF input and all of a sudden magically the function generator starts producing a different frequency. So this is a diagram that we have here. We have our oscilloscope here, our function generator here. We've got the output of the function generator and the VCF input to the function generator. We can have a DC power supply over here. We supply a common ground for everybody and hook everybody up to that common ground. We take the power supply's DC output and hook it up to the VCF input of the function generator. We take the function generator output, we hook it up to our scope, and we watch the square wave. So now, if you want to change the frequency on the function generator, you can watch it on the scope. You come over here to the DC power supply and you turn the DC power supply knob, and all of a sudden you see the spacing in between the peaks change on your scope. without having to physically touch your function generator. You're using a voltage to control the frequency of the function generator. Okay? So now what we've done is we've just changed the ability the ability to alter the function generator's frequency. We don't have to touch this thing's knob. We have to touch this thing's knob. We have to now touch the DC power supply's knob. Well, that's a step in the right direction, but still not quite there yet. Okay. One question you need to address in the lab is how much of a change in voltage on the VCF input results in how much of a change in frequency on the output of the function generator. So this is a calibration step you need to perform. So what you need to do is hook this up in your lab, and you got your DC input. You hook it to your VCF, and you tweak the knob on the DC input. How much of a change in voltage gives you how much of a change in frequency? And then you need to hit the different buttons on the function generator. Does it change if you're at 10 kilohertz, or if you're at 100 kilohertz, or if you're at 10 hertz, etc. Okay. So calibrate it, or in other words, measure the performance of the device. Okay. Unfortunately, we're still in a situation where a human has to turn a knob in order to impact the frequency that we're outputting. Now, what we want to do is, instead of having a human turn the knob, we want to have a TS7200 turn the knob. Why do we want to have a human to turn the knob? Well, the turning of the knob effectively means we're impacting the motor. So we have to have these two guys, no human, no hand, nothing up this sleeve or that sleeve. We want the TS7200 to be able to adjust the frequency. Okay, and again, remember, this frequency represents the velocity of the motor. So by being able to adjust the frequency, we are emulating the adjustment of the speed of the motor. Okay. So if we want to use the TS7200 to change the frequency of the function generator, how can I do that? Well, what can I output? I don't have a digital to analog converter. What I do have are digital I/O pins. It's not to say that the TS7200 can't output to a DAC, we just don't have one on there. So what we do have are digital input pins, digital output pins. There's the DIO pins, and we've already seen that you can supply an input to the TS7200 that ranges between 0 and 3.3, those two voltage levels, low and high. I can configure one of the DIO pins to be an output pin, and so I can output a 0 or I can output a 3.3. So with these two signal levels, maybe I can associate with the 0 volts the concept of don't change. So if I have the TS7200 output of 0 volts, that means tell the function generator don't change anything. Or in other words, the VCF is at 0 volts, so that means it's going to output the nominal frequency that it's already set to output. If I want to change its frequency, maybe I hit it with a 3.3 volts, and that tells it change your frequency. So change or don't change. I have two levels, and so if I apply a 3.3 volts to the VCF, that will adjust drastically the frequency that the function generator outputs. But I only have the two levels. I can either go the nominal level or massive change. What if I want to slow it down? Okay, so let's suppose, and I'm not telling you exactly what the 3.3 volts does because I want you to calibrate what the VCF input, what the impact of the voltage on the VCF input does. But suppose the 3.3 volts were speeding up. You can't use a positive voltage to both speed up and slow down, but you can either go regular or faster, perhaps. Or regular, maybe this is slower. You're going to have to discover which one that is. But let's suppose that it's go faster. Well, what if I actually want to slow down? Or if I only want to speed up just a little bit? And that's not necessarily effective by just having two settings on my digital I/O output. So how can I break this down and do a more fine step and more fine steps? Okay. Okay. So what I want to do is, okay. So here's the example. What if the 3.3 volts applied to the VCF results in a 2 kilohertz jump when all I want is a 100 hertz jump? So how can I step in smaller steps? Can I use a digital I/O line to make more fine-tuned adjustments? So for what we're going to do next is we're going to consider a low-pass filter. I thought this was a software class. Why are you showing me a resistor? Sorry. Okay, so we've got an AC input going into a resistor. That goes into a capacitor. We're going to take the output in between the resistor and the capacitor. I assert that this is a low-pass filter. I hope you all already understand this. This is something you should have had in the beginning circuits class. But basically, when this sinusoidal signal has a very low frequency, what that implies is it takes a long time for the capacitor to charge. It effectively acts like an open circuit. And so we just get if I have a very low frequency here, like a DC value coming in on the source, the capacitor acts like an open circuit, and I just pass through whatever this source is telling me. If I have a very fast sinusoidal signal, the capacitor charges and discharges very frequently. It effectively acts like just a line, just a wire, and ties that to ground. So what I end up with is an output value that's always 0. So that's what the justification of this frequency curve here. This plots the frequency response of that circuit. You've got this pass band here where for a certain level of signals, when the frequency is low enough, the output is just whatever the input signal is. Over here in the area where I do rejection, if the frequency is fast enough, then I see complete attenuation of the input signal. In this input range, I see some attenuation, but it doesn't attenuate it completely. So where is this point right here? Where's the end of the pass band? Where's this point out here when I have complete rejection? Well, it depends on the values you pick for your R and your C. Okay? And you are going to have to do, unfortunately, a little bit of circuit design. You guys get to pick your own R and C for this lab. Okay. What does a low-pass filter circuit do to a square wave? Let's suppose you got a zero mean, 50% duty cycle square wave, and you throw it through your low-pass filter. What is it going to do? Anybody care to guess? Anybody know? How many of you have not had a circuits class? All right, so therefore I can call on any of you to tell me what this circuit's going to do, right? My head hurts already. Okay, what's it going to do? Smooth it out. Okay, a low-pass filter circuit is also an averaging circuit. What it does is it'll replace the value of your value of your input signal with the average value of that input signal, supposing that the frequency of that input signal is fast enough. Okay, so for fast frequencies, we replace that signal with the average value, the average DC value. Because this is a zero mean signal, we end up with a 0 volt output. What does it do for slow frequencies? It'll slowly charge the capacitor, and eventually the capacitor will get charged, and then the input value will change, and it'll slowly discharge the capacitor. So it'll have this rounding effect on the square wave pulses. And depending on how fast or how slow the square wave is, this becomes more pronounced or less pronounced. So, but you will see some slight alterations on the corners. Okay, so these slow transitions are because the capacitor is charging and discharging. Medium frequencies, you'll see the capacitor start to charge, and then you'll turn the voltage input value around, and so the capacitor will start to discharge, continue to discharge, then it'll start to charge again, and discharge and charge and discharge, so it turns into a triangle wave. Okay? All right, so the low-pass filter circuit really is an integrator circuit or an averager circuit. For high enough frequencies, it replaces the square wave with its average DC value. Okay. What does it do to the following here? This guy here where we've got not a 50% duty cycle wave. So if this were 50% duty cycle, it would be zero mean. But if it's not 50% duty cycle, what does that averaging circuit do to this square wave? So let's suppose that the RC is big enough to convert this guy into DC. What will its DC value be? Would it be positive or negative? Would it be just barely negative or a lot negative? Close to 10 or close to 5, close to 1, minus 1, minus 10, minus 5? Probably be pretty close to minus 10. Okay, because it will replace it with its average value. So the capacitor mostly stores the minus 10 value. Sometimes it is forced up to the plus 10, but because of the fact that our RC value is big, and it'll allow this guy to pass through as a DC value, basically what it does is that occasional tick up to the plus 10 just pulls the average value up off of the negative 10 rail just a little bit. So it'll be close, but not quite negative 9. How about this guy? What's its average value? Around 10. Occasionally we have the negative dip, so maybe around negative 9. Maybe it'll be the average value will be around positive 9. So what you can see, the difference between this wave right here and this other one is the fact that we have changed the duty cycle. We haven't changed the frequency of the wave, we've just changed the duty cycle. So if we just suppose that one frequency or one period of this wave is, if we just chop it up into little chunks, and we count up how many of those chunks are at the positive rail and how many chunks are at the negative rail. If we have as many positive as we have negative, that's a 50% duty cycle wave. If we have all but one of them be positive and only one of them be negative, that's what we have with this wave right here, where we have changed the average value of this wave to be as positive as we can. We can't just let them all sit positive because then we don't have a square wave anymore. So, and then the converse, where we have as many ticks low as possible but still retaining a square wave, that's what we have on this upper one, where we have the average value of the circuit being as negative as we can. So we just alter the duty cycle. Okay, so now what we have here is another setup. So this is our function generator here with our VCF input and our output. Here's our scope where we're watching the output of the function generator. We've got our TS7200 down here. And now the TS7200, remember, what its job is to do is to sense the frequency. So we're just using the TS7200 in this context. It's kind of redundant with the scope. We're just using it to measure what's the frequency of our input. We haven't used it to actually output anything yet. So we're just sensing the frequency of the input, just what you're doing with Lab 3 Phase 2, but correctly. Okay, so this function generator has the VCF input. Here's our integrator circuit. Our integrator circuit is outputting its output to the VCF input. So the idea here is that the integrator circuit will take whatever comes into it, iron it out to DC, its average value, and send it to the VCF input. What do we supply as the input to the RC? Well, we can use another function generator to create a square wave that we can then send into our integrator circuit. So here we supply the duty cycle knob. We tweak the duty cycle to be either a mostly positive wave or a mostly negative wave, and we can see what are the various values of DC that we get out for our integrator circuit. And by varying the duty cycle on that function generator, we can vary the frequency on this function generator. Okay? So here's a step closer. So now instead of having a human tune the knob of a power supply, now all we have to do is turn the knob of the duty cycle over here on the second function generator, and we can control the frequency of our other function generator. But we still have Captain Human over there turning a knob. We want to use the TS7200 to turn the knob. So now all that you have to do is just implement a robotic hand that will go through and turn that knob, and that's Lab 4. Okay, maybe not. All right. So all that we've done in here is we've just used a function generator and an RC circuit to replace the DC power supply. Again, how big of an R and a C? That's up to you. Big. Okay. So we still aren't quite there yet. We want the DC motor to be controlled by the TS7200. We've shown how the TS7200 can receive digital input signals, but what I haven't shown you yet is how the TS7200 can output digital I/O signals. So part of the Lab 4 code that I give you is some code that will output a digital I/O signal. You can, in software, write a value to a memory location which will cause an output pin to output either low or high. Okay? So the software that I'm going to give you will just take one of the digital I/O pins, configure it to be an output, and we'll write a value to that pin to say be high or be low. Okay? If you do this periodically, all of a sudden you can make a square wave. So if you have something like this, so you say for forever, t equals t time, all t time, wait, toggle pin 1. So here was the difference between last year's notes and this year's notes. These two next guys shouldn't be there. Okay, so if you say, wait for a pit, toggle the pin, wait for the pit, toggle the pin, wait for the pit, toggle the pin. You don't want to wait twice. But this is similar to the code that you've already seen in RPM.C, right? So you're going to wait for a tick, then toggle the pin. This over here would wait for another tick. So you would have you toggle the pin value and hold it there for 2 ticks, then toggle the pin and wait for 2 ticks, then toggle the pin and wait for 2 ticks. If you remove one of those, you wait for a pit, toggle the pin, wait for the pit, toggle the pin, and you have a 1 pit period toggling. So it looks like this. So every time pit fires, if you have a scope on your output digital I/O pin, you have 3.3 volts, then the next pit you have 0, then 3.3, then 0, then 3.3, then 0. 1 pit for each state change. Okay? 1 period covers a high and a low. So our square wave has a period that's equal to 2 pit periods on this guy. Okay? So now you can have your TS7200 board be a function generator. Okay? You can tweak the code to do something like this, where instead of waiting for 1 pit period, you wait for 2. Then you toggle the pin, wait for 2, toggle the pin, wait for 2, toggle the pin, wait for 2, toggle the pin, and so forth. You can carry that out to the next extreme and say, well, how about we wait for 16? So we'll leave it high for 16, then toggle the pin, wait for 16, toggle the pin, wait for 16, toggle the pin. So now you can create an output square wave that has a 50% duty cycle that consists of multiple pit periods for the square wave period. Okay? Can you change the duty cycle? Well, sure. Why can't you just toggle the pin, then wait for 2 cycles, then toggle the pin, wait for 1 cycle, toggle the pin, wait for 2 cycles, toggle the pin, wait for 1 cycle, toggle the pin. So all that it is you just change when it's high and when it's low, and you just change how often you wait while it's high and while it's low. So you can have 1 up, 3 down, 1 up, 2 down. If you're going to maintain a 32 tick period wave, then you would have, you're going to have the wave be high for a certain number of ticks, and then it'll be low for a certain number of ticks. And the high count and the low count has to sum up to 32, but you can vary how often it's high and how often it's low just by varying your counts. What do you do when you integrate this wave right here, where you got 1 up, 3 down? What's the average value of that? You're telling me it's a third. It'll be a fourth, 0.25. A fourth of 3.3. What's 3.3? 3 1/3. What's a third of 3 1/3? 17. Sounds good to me. Anyway, what you're going to do is you're going to take your voltage range over here from 0 up to 3.3. Different duty cycles will correspond to different DC average values in between these levels. And what you're going to have to do is churn out different duty cycle waves, send it through your integrator circuit, and see what values of DC you're getting. And then also for different duty cycle waves, send that through your function generator's VCF input and see how much of an impact it has on frequency. And now, all of a sudden, because you can take your duty cycle, vary it, and apply it to your function generator, you now have your robotic hand with a latex glove on that will change your frequency for you. Okay? So you have your function generator here with your VCF input, your output to the scope, and also to your TS7200. Your TS7200 is sensing the frequency on this line. It's sensing it with the same techniques you're using in Lab 3 Phase 2. Okay? You also have the pit timer running in here. Okay? At the same time, we have on DIO1, this is the output pin to the TS7200, you're generating your square wave, varying the duty cycle according to whatever needs to be done. So you have your output that goes over here to your integrator circuit. Your integrator circuit sees the square wave, replaces it with its average value. It's a nice iron for your nice white shirt. So you iron out the variance in that input signal. You get a DC value. That DC value applies to the VCF. Supposing that you output a value on your output that ends up not changing your function generator's frequency output at all of this just goes on normal. So what we're doing is we're applying a voltage here, but let's suppose that we apply a voltage here that adjusts our output to be what we want it to be, and we hold it at that value, everything's happy. So let's suppose that the user comes along and says, well, you know what, I don't want the frequency to be what you have it at. I want it to be, 10 kilohertz more. So you can decide that you want to be 10 kilohertz more. Inside your TS7200, you'd have to do some calculations to figure out, I know what my frequency is, I know what I want it to be, what type of change in the duty cycle output on DIO1 do I need to make in order to get that 10 kilohertz increase in frequency to be. So I change the duty cycle here, that would impact the voltage level here, that would impact the frequency that I'm outputting there. So as long as I do that tweaking enough and appropriately, I would see a change in the frequency on the scope. Alternatively, what you can do is you can tell the TS7200, no matter what happens, I want you to maintain your set point to be 100 hertz. Okay? So it will be constantly sensing whatever the input frequency is, and as long as it can sense it with sufficient accuracy, it will say, okay, well, I've got 100 hertz, that means no adjustment on my output. But what if you come along on this function generator here, you grab its knob and you turn it a little bit? What you've done is you've introduced an error into your system. And so then the TS7200 should see that, should sense that error, and it'll say, oh, I'm not at 100 hertz anymore, I'm at 300 hertz. I need to react to this. So what it should decide is, what do I need to do to bring the frequency down by 200 hertz? How do I calculate that in terms of a duty cycle? And that gives me what change in the duty cycle do I need to make. I send that out to my integrator circuit, producing a DC value that will apply to the VCF input that will alter the frequency that the function generator is outputting and will bring me down to 200 hertz. How do you make the decision on the TS7200 of how much to adjust? You're going to use a PI controller algorithm. You've used a P controller in the last lab. This lab is going to use a PI controller. And I've given you the algorithm of the PI controller inside the lab write-up. Okay. This idea of using a square wave and integrating a square wave is called pulse width modulation. It's very common in embedded systems. Okay. So, if you can't tell already, this lab involves lots of steps. And it's quite involved, and it's going to take a lot of time, and you are, unfortunately, like it or lump it, now married to Engineering 328. You have to do most of this lab in that room because of the fact that it's got the function generator, the power supply, and the scope. Okay? You can do a lot of your software design outside of the lab, but this is going to require a lot of testing and calibrating and benchmarking and examining what's going on and trying to understand all the various steps. I've written the lab write-up out in a series of 10 different things you need to do and what you need to examine. So follow the lab write-up in this. Okay. The last thing you're going to need to do after you get all this working is make it work in the background. So you're going to have a user interface that you're going to print out to the screen, and that's going to have to go up to the user on your host machine where the user can type in, I want you to change your set point frequency to this. And so that will have to be, your TS7200 is always going to have to be scanning its input port, making sure that if the user sends a command down, it has to process it. But all the control stuff has to go on in the background while the user is able to type his command. So, that's lab 4. Not too bad, huh? So, you've got lab 4 will be posted today. Then the review session today at 2:30. I will not be here tomorrow because I've got to go down to Hill Air Force Base for a meeting. And then we will have the take-home exam on Wednesday. We'll give out the exam after class on Wednesday. So we're going to have regular old lecture on Wednesday, and then the midterm exam will happen after. Okay, questions? All right, thank you.
Wow.